We stopped around here yesterday where we wanted to address the simplest problem probably in combustion of premixed reactants. And this is a planar flame steadily propagating into the fresh mixture. And so the governing equations that were put in non-dimensional form are framed in this box. We discuss all the parameters, and including the expression for the dam color number D. And essentially what we are faced is solving this nonlinear problem. In other words, solving for the temperature, the mass fraction, as well as this unknown D, which is known as the burning rate eigenvalue. It's an eigenvalue problem. In other words, that's part of the unknown is to determine this D. And just to remind you, the D contains the laminar flame speed, so that once we know D, we can write an expression for the flame speed, and that's the objective of this discussion, this analysis. So we focused on the reaction rate, and I have fixed few of the things that we sort of left yesterday. In other words, I kept it until when I reduced it into a two-component mixture as I started the discussion with a fuel and oxidizer with different reaction order. But that's not the important factor. The important factor that we have focused on is the exponential. And we have seen that since beta naught, which is the activation energy parameter, can be treated as large parameter, then the flow field in general is divided into two regions. A preheat zone where the reaction rate is very small and negligible. In fact, it's exponentially small because you see the exponent written this way. When T is less than TA, the adiabatic temperature, since beta naught is large, 10 to infinity, then this is like e to the minus infinity, which is approximately 0, very small. And so it's negligible in the preheat zone. But of course, when T is close to TA and it's close to within 1 over beta, then the reaction becomes important, and this is in this red region that we refer to as the reaction zone. That's where omega is not negligible. And then beyond that, you have the burned gas where there is no more reactant, so nothing happened, and obviously the temperature will stay the adiabatic temperature because it's an adiabatic problem. There is no heat loss. So with this kind of simplification, then we are going to proceed. And this is essentially in words what, now, I have used this, so far, this parameter beta naught, which was defined as the activation energy divided by the unburned temperature. Now, it turned out that after you carry on the analysis, that the most appropriate or the more appropriate parameter for expansion turned out to be this quantity. In other words, it's multiplied by this factor TA minus TU divided by TA squared, which is approximately something like 1 over 6, 1 over 7. So it's an important factor. And this parameter is often referred to in the literature as the Zeldovich number, beta. Now, I must tell you that, in my opinion, this is a parameter that it's the appropriate one for premixed flame. Sometimes people use it for diffusion flame, and I don't think it's quite right because there is no really origin or need to include this factor. But anyway, that's a minor point. I'm not going to dwell on this. Now, there is a relation, of course, that you can write between beta and beta naught, and that's the reason why originally I call it beta naught, just to distinguish between the two. And it's this factor where now, remember the tilde are all dimensional quantities. This is the dimensionless. And so you can see the relation between the two. Now, if you look at the exponential and replace beta naught by beta, of course, the form of the exponential is a little different, but it has the same nature, namely, when t is less than ta, this is exponentially small, and only near the reaction zone, where T is close to TA, it becomes in a region which, when T is close to TA within 1 over beta, then of course that becomes an order 1 quantity. Okay, so this is just a rewrite of the same thing that we discussed before. There was one minor comment that I wanted to make, and I don't remember what it was now. And so, oh yeah, here it is. So beta typically is around 10, the Zeldovich number. Beta naught clearly will be larger, and it's probably around 70 or 80 or so. But it makes no difference. We are assuming that either beta or beta naught are large, and in both cases it's appropriate. So the problem now is framed here, but I have taken one more simplification at this stage, and this is to consider a mixture which is deficient in one of the components. In other words, to focus at the moment either on a lean or a rich mixture. So if it's lean, Y is the fuel. If it's rich, Y is the oxidizer. In other words, I am focusing only on one reactant. And I will give you the answer later on for 2 reactants. It's just that it's simpler to see the mathematical development when it's less complicated with details which are not crucial. And therefore, since we, equivalently, it's like talking about a case where reactant go to product, and the other reactant, namely either the fuel in a rich system or the oxidizer in a lean system, is in large quantity, doesn't change much during the reaction. And equivalently, it's also taking NF to be N and NO to be 0. So you can think of this as being a 0 order in the reaction, a 0 order with respect to the oxidizer, if you like. Well, they are all equivalent. Okay. So the main point to make, though, is that the Lewis number here, therefore, should be carefully interpreted. It should be the thermal diffusivity of the mixture divided by the mass diffusivity of the deficient reactant, right? Because in writing the equation in this form, Y is the reactant which is the least in the mixture, and so the Lewis number will be the Lewis number corresponding to that. So in lean mixture, the Lewis number is the fuel. In rich mixture is the oxidizer, and we're going to see that that will become important at some point later in the discussion. So, now, since the reaction term is negligible, except in the reaction zone, we can solve the problem in the preheat zone, and we assume an expansion in the small parameter, which is beta to the -1, and if we calculate the leading term in the expansion is essentially by setting the right-hand side to 0. Incidentally, the right-hand side, being exponentially small, is therefore negligible to all powers of beta -1. And so I can compute this expansion to any orders that I want. But really, it's not important. The main one that we need is the leading term, and it's written here, where the solution I have assumed already that the temperature and the mass fraction are continuous at the reaction zone, something that you anticipate or expect on physical ground. And so you see that when, and furthermore, we have assumed that without loss of generality, that the reaction zone is at x equal to 0. Of course, it's an infinite problem, and so you can set your coordinate where you want, and so I can set the origin to be where the reaction zone is without any loss of generality. So x equal to 0, it's where the reaction is, or at least the vicinity of x equal to 0. And so at x equal to 0, e to the 0 is 1, and that reduced to TA. So you see that it's continuous, as well as this is 0, so the mass fraction is 0. And so that's a good solution that is to leading order, which is valid in the preheat and beyond the reaction zone. But this solution is not valid near x equal to 0, because near x equal to 0, the temperature T is close to TA, and we have seen that when the temperature is close to TA within 1 over beta, then the reaction is important. And so we know how to scale the coordinate x in order to catch up this changes or the effect of the reaction. And the stretch has to be, in other words, we have to zoom on a region near x equal to 0, and the zooming is by scaling x with the power, with the small parameter beta minus 1, as we shall see in a minute. Before we go there, there are certain things that we can obtain without looking at the reaction zone itself. So for example, if you look at the two equations, you add them up after multiplying the second one by q, and integrate this equation across the reaction zone. In other words, you integrate from 0 minus to 0 plus. Then you immediately, because the solution is continuous, which means that the jump in t across the reaction zone and the jump in y across the reaction is 0, has to have the same value on both sides, then immediately this drops when you integrate it, right? And I'm sorry, the first derivative drop because when you integrate you get t plus qy, and the only contribution comes from this term which is written here. And that immediately tells you that there is a relation between the energy flux into the net energy flux, actually it's out of the reaction zone, right? And the net fuel flux into the reaction zone. And that is expressed in this jump relation here. So that you can obtain without even looking at the detail of the reaction zone. However, what is that flux? We don't know. And that is exactly why we have to examine the detail inside the reaction zone to determine that flux. And that's what we are going to do next. So here is the solution. That's another little detail. The solution, we have already assumed continuity. What if we now apply this flux relation that I have mentioned before? Well, when you apply it to the solution, you obtain that the flame temperature, the adiabatic is the adiabatic flame temperature, which is 1 plus QU. So it just shows consistency here because we have already obtained that value, the flame temperature, from more or less in a similar way. What we did, we integrated across the entire domain except instead of across the flame, but it's essentially the same information. So it's not surprising that we are getting the same information. It's consistent, it's very good. So now we have to zoom around x equal to 0, which means we have to scale x in this form, beta minus 1 xi. So xi is an order 1 quantity. It goes from negative infinity to plus infinity. So when xi is very large and negative, it's multiplied by a small parameter, so x becomes an order 1 quantity on the negative side. And when xi is very large and positive, the product here gives you a quantity x which is positive, but a little bit off 0. So essentially, this xi is the scale on this shaded region here, which is of order 1 over beta, and it goes from negative infinity to plus infinity. The curves that you have seen here, the black curves, is this solution, and what is missing, what we need, is to smooth out the solution in that thin region, and the way that we do that is by, as I said, by zooming in this region and rewriting the equation as appropriate in the new scale in this region. That's something that we shall do next. Okay, so here is what we do. The temperature in that region is clearly near the adiabatic, so we write it T adiabatic plus a correction. So phi is the correction in the reaction zone, and y, which is the reactant, is 0 to leading order plus a correction, which is expressed as psi, okay? And both phi and psi are a function of xi, and now we want to see what equation that satisfies. So we substitute this into the governing equation, right? In addition, well, you can do it in two ways. Either you substitute and then determine the magnitude of d. What I did, I already determined what the magnitude of d is in order to get the term balance. In other words, what it means is that the eigenvalue also need to be expanded. A priori, we don't know how to expand it. The way to expand it is to ensure that whatever is on the left-hand side that remains, order 1, have to be balanced by something on the right-hand side, which is the reaction, which should also be order 1. Okay, so now we make that substitution, including the stretching. Now the stretching immediately tells you that since x is equal to beta minus 1 xc, then d by dx is d by dxc by dx, which is dxc by dx, which is beta. And so everywhere we replace d by dx by d by dxc beta. And after we multiply through, because there is another beta minus 1 that show up from here, and there will be beta square in the second derivative, only one beta here. When we multiply through, we see that the convective terms are multiplied by beta minus 1 as opposed to a factor 1 here, so those are small compared to diffusion. In other words, convection in this thin region is negligible compared to diffusion. And what balances diffusion is the reaction term with the rho b is essentially the density at the reaction zone, which is the burn value. So that's a constant. The mass fraction of the reactant is psi, and the temperature, exponential temperature, which is here, after you substitute for T minus TA beta minus 1 phi, you obtain essentially it's proportional to e to the phi, divided by a constant. So these are the two equations that remain to be satisfied, and this capital lambda is just a rescale of the eigenvalue, the burning rate eigenvalue. Okay, so now we have to solve these two equations. Well, we have second order equations. They are, by the way, nonlinear, and you have to solve them on a range from minus infinity to infinity. But what boundary condition to use? Well, this comes from what is called asymptotic matching. And matching, just, I mean, this is a whole course by itself, match asymptotic expansion, but just to say in few words, it's not patching. In other words, it's not the same as saying that at a certain point we want the two solutions to have the same value. That's patching. And patching is not good enough because then it has arbitrariness in where you patch the solution, and that's not a quantity which is part of the problem. Matching is just that the two solutions just blend into each other. They have, in a certain limiting way, they tend to each other. And you can see that in the picture that I put here. You see that the red solution tend to the black solution. In other words, it would have the same slope in the limit and the same slope in this at this end. And so the two solutions have to match into each other. Those of you who are familiar with boundary layer, it's exactly the same thing that you do in boundary layer. You try to match the viscous layer with the viscous solution in the boundary layer to the inviscid flow outside. And again, it's a matching process that you do. Okay, having said that, here is a quick version of how you do matching. Well, you look at the solution outside the reaction zone, and you say, well, when x approach 0 from above or from below, then I can expand the exponential in a Taylor expansion. So instead of e to the x, is going to behave like 1 plus x. And so if you substitute that in here, you obtain that this is the behavior near 0 minus, and this is the behavior of the solution near 0 plus. Similarly for y. Therefore, phi and psi must have the same nature, the same behavior as xi goes to negative and positive infinity, where the difference between here and here is just introducing the fact that x is beta minus 1 xi, and that phi was, as you recall from before, the deviation from TA, right? And so that's exactly the boundary condition that you have to apply at plus and minus infinity in order to solve this equation. So I will run quickly through, well, here I just rewrote the problem, the phi equation, the psi equation, and the matching condition. But because this is the behavior of the solution at plus or minus infinity, in fact, it involves, every statement here involves two statements. It involves that phi behaves like this, but also the derivative of phi with respect to xi is Ta minus 1, okay? There is a minor detail that I'm going to skip because in principle one can add here a constant, but that constant can be chosen 0 without loss of generality, and I'm not going to discuss it. Those of you who are interested can probably find something about this in the literature. Where exactly, I don't know, but I know that I have written something on this somewhere. So anyway, if you come back, this is the two, you see here you have both the slopes as at negative infinity as well as plus infinity, but in addition at plus infinity, both phi and psi must vanish, right? Because the temperature is adiabatic and the concentration is 0. Okay, so these are the equation, and in principle, the solution will look exactly like you see here, okay? They start at negative infinity with some slope. This one is positive, this one is negative, right? And they tend to 0 as you approach infinity. So you can, in principle, solve this numerically if you like, but the advantage of finding some analytical part or analytical answer from here is great because it will allow me to get an expression, a clear expression for the laminar flame speed, as you shall see. So the first thing to do, since these equations don't have any convection term, you can just multiply this one by q and add them together. You'll see then that the right-hand side vanish. So you have some kind of coupling function which is valid only in the reaction zone. And that coupling function, because the slope and the function need to be 0, satisfy that the sum is equal to 0, which means that phi is related to psi. So if I know one of them, I know the other. And so I can substitute for phi instead of phi psi, and then I have a single equation to solve for psi, and this is what is in this box. So that's a single equation. Note that here the phi that was in the exponential before is now a psi. Now this is a nonlinear equation, but it's one that at least the first integral can be obtained very readily, and the way to do it is just to multiply both sides of the equation by the first derivative. Because then the first derivative times the second derivative is the derivative of the derivative squared, right? Because if you differentiate this, you get 2 times d psi d xi d2 psi d xi2, which is exactly what the left-hand side will be. And then you integrate this from negative infinity to plus infinity, which means across the entire reaction zone. Well, again, those are details how you do it. The calculation of one integration gives you that the right-hand side can be evaluated. This definite integral is the so-called the gamma function, which for an integer is just the n factorial. It's a factorial function. For a non-integer, you know, it's well defined. There are tables that you can find it in mathematical tables. So it's a well-defined function. So that's a number, okay? Now, if you put it since we know what the psi d xi is from the matching condition, we end up with a simple relation for the eigenvalue, the burning rate eigenvalue lambda, which take this, this form, okay? Now you may ask me, okay, why, okay, how about integrating a second time in order to verify that indeed the solution has that form? Yes, you can, but unfortunately the second integration become implicit. In other words, you will write the answer as xi equal to some function rather than phi equal to some function of xi. You can do that, and you have to do that to just verify that a solution does exist, because otherwise we're not guaranteed that such a connection is possible, right? Okay, so that is not written in those notes. But this was done, and part of it is clearly numerically, but this is now, the focus is on the on the burning rate eigenvalue. Now remember I told you that capital lambda is essentially related to the Dam-Koller number d. So if we know lambda, we know d. So now this is what we are doing next. we know lambda, we know d, and since d by definition involved the laminar flame speed, we end up with an expression for the laminar flame speed. So here is the expression for the laminar flame speed. It's written in everything here with tildes, so they are all dimensional quantities. The adiabatic flame temperature in dimensional quantity is this, and the flame thickness, or at least the measure, the representative flame thickness, and I'll make a comment about this soon again, is just the thermal diffusion length, which is just given by that. But remember, it involved the laminar flame speed, so until now we didn't really have a full description of the thickness or a full identification of it. Okay, so, and remember that this was written for any reaction order n, but for only a single reactant. And I will tell you a little later the same relation, how it's modified when you look at two-component mixture. Okay, and now just a simple comment, which is actually quite important. If you look from the matching conditions, or at least remember I told you that you can get a lot of information by integrating the equation across the reaction zone. But what you do not get is what is exactly that flux. Well, now that we have solved the problem, in fact, we have an expression exactly for the flux. For example, the flux of fuel into, and it's a diffusion flux, right? Which is the diffusion flux into the reaction zone is given by this expression, which has this lambda, which now we know what the value of this lambda is, okay? And what this is actually nothing more than the integral of the reaction rate across the reaction zone. But since the reaction is negligible outside, it's also the integral of the reaction rate across the entire domain, which is sometimes referred to in the literature as a consumption rate or consumption speed. So this is related clearly to the flux, and the flux is related to the speed, so everything is clearly consistent with that. I will come back to this relation later when I will summarize the main outcome of the asymptotic solution. But now I want to go through some comments that, and then try to understand the nature of that expression, which is the laminar flame speed and related to experimental observation. So the first thing is, so the most of the reaction occur in a narrow temperature interval of near TA, which is adiabatic temperature, which is of the order of beta minus 1 LF. That's the reaction zone thickness. So if LF is typically a fraction of a millimeter, then the reaction zone is 1/10 of that, so it's much thinner. Okay. Beta, remember, was like 10. At least for most hydrocarbon, it's a good approximation. The preheat zone is the region where the temperature rises from TU, the cold temperature, to approximately TA, which is the adiabatic temperature. Most of this increase, like 99% of it, occurs in 5 unit lengths because you see the solution is, where is this? Here is an exponential, right? And if you take the exponential of 5 units, you obtain it's approximately 0.01. So the drop of the temperature from this point to nearly the cold temperature is approximately over 5 units of LF, the diffusion length. So the true flame thickness is 5 LF, it's not LF. So when you read in some places that people say, oh, but the asymptotic solution gives you a flame thickness which is not physical, it's nonsense. The flame thickness is 5 times LF, it's not LF, okay? That, remember, there's a factor there. It's just LF, it's a representative value for the non-dimensionalization. Now, of course, there are different ways. You can argue that there is some arbitrariness in this because I chose 99%, and I could have chosen a different isotherm to represent the cold edge. But there is also arbitrariness in some other definition that people are doing. For example, but it's unavoidable. You have to do it, of course, in some way. For example, you take the inflection point and you define the flame thickness to be a region, say, between when that hit the asymptote or something like that. Well, there is an arbitrariness here as well, okay? And it's not clear how much of the full reaction zone that catch, okay? So you have to define it in a certain way. By the way, in boundary layer theories in fluid mechanics, you also define your thickness of the boundary layer in a certain way, and you have to make a choice how you define it. So it's the same idea. Okay, so, oops. The next item is that I could have generalized all this discussion by allowing for lambda, the thermal conductivity, and therefore all the diffusivities, because we have seen that they are all related, and it's enough if lambda is a function of t that covers transport that is temperature dependent. I could have generalized that solution quite easily. All I had to do is just, instead of e to the minus x that I had in my answer, it's going to be the integral of 1 over lambda dx, okay? And clearly, well, lambda is clearly here dimensionless. In other words, it's scaled with respect to the conductivity of the, say, the unburned gas. And so when lambda is 1, of course, you recover the previous solution. Lambda doesn't vary in temperature. Otherwise, there is a slight variation. And the change in the flame speed expression is going to be to evaluate lambda in that expression with the value on the burn side, because that's the most important region where the flame speed relation came from. And so that's easy to do. Now, we have solved for t and y, but of course, we have two other relations from which we can compute the rest of the solution. For example, from the equation of state, rho t equal to 1, we can compute rho, right? Which is going to be 1 over t. And from the continuity equation, rho u, we can compute u. So u is going to be proportional to t, and rho will be inversely proportional to t. In other words, the gas expansion, as a result of gas expansion, the density decreases, and as a result of that, the gas speeds up, okay? Then finally, the pressure can be obtained from the momentum equation. Since we know the velocity, all we have to do is to integrate the first order equation for the pressure, and we can write an expression for it, which in fact tells you the slight drop in pressure that occur across a deflagration wave. We have seen, remember the discussion of deflagration and detonation, that the pressure decrease across a deflagration, right? And so we can compute that. Now let's focus first on the flame speed relation for the case where n equal to 1. So for n equal to 1, this function gamma of n plus 1 is n factorial, n equal to 1, 1 factorial is 1. So that's, that's n equal to 1 is gamma of 2, and n factorial, so it should be gamma of n plus 1, I think it's n factorial, so it's 1, right? So that's simple. But anyway, it's trivial, it's just a number. So here is the expression, and just to show you how good that expression is, or how not good it is, however you want to characterize it, I have plotted here the asymptotic value and the numerical value. In other words, if I were to solve this problem numerically, and the ratio numerical versus asymptotic is represented in the axis as a function of beta. Now remember that in principle, strictly speaking, the asymptotic solution is valid when beta is large. In other words, the solution becomes more and more and more accurate the larger beta is. in principle, if beta goes to infinity, the two must tend to the same value, and it does. Okay? Now the question is how good the approximation is for, let's say, beta equal to 10. Well, the result here show that it's good within, with the exception of the Lewis number equal to 2, it's about 5 to 6%, and it's quite reasonable. But that's not really the important thing of the asymptotic solution. The important thing is that we can verify, or we can see the dependence on every one of the physical parameter, and that's something that I will discuss next. Before that, I want to show you that there has been a derivation of the second term in that expression. In other words, carrying on this asymptotic sequence, or asymptotic perturbation, to a higher order. And one finds that in addition to this factor, which was here, there is a correction of the form 1 plus something beta to the minus 1. Now, to show you how that does, then what is plotted here, it's a numerical solution divided by this leading factor. So what I'm comparing is, in fact, between numerics and asymptotic of what's in this square bracket. Okay? The solid curve is the asymptotic, the dotted, I think, and the dotted curve is, or the dashed curve is the numerics. And well, actually, it should be, oh, it's not here. I think that that's correct. It's not written, but at any rate, it doesn't quite matter at the moment which is which, because all I want to show you is that they're quite close to each other and closer to the error that we have seen before. So with that said, let's just make the last point written here, that the flame speed show a very strong dependence on the Arrhenius rate, in particular on this exponential, because any slight change in the adiabatic temperature make a significant change in the flame speed. It's enough to change TA by a quantity which is like 1 over beta naught. In other words, a small change of maybe a few hundred Kelvin to make a significant change on the flame speed. And that's what this expression, in fact, show. Okay, so now I want to, before I focus back on that equation, here are the few generalizations. Suppose that we look at a two-component mixture. In other words, we have fuel and oxidizer, but we have assumed here that the reaction orders are 1 with respect to the fuel and 1 with respect to the oxidizer. So it's 2 overall. Then the difference is really in this additional factor that I called S. S stands for effect of stoichiometry, and the phi here is the equivalence ratio. So for a lean mixture, you see that this is the change that you would anticipate. For a rich mixture, is this, and in particular, at stoichiometry, when phi is equal to 1, since this term becomes small, being multiplied by beta minus 1, then the two expressions collapse into this. The difference between, let's say, the expression for a single reactant and this other relation can be seen also by the fact that instead of the Lewis number of the deficient reactant here, which appear in this expression, the two Lewis numbers now appear, both the fuel and oxidizer, at stoichiometry. When you are not at stoichiometry, then one or the other will weight more, and you can verify it. I am going to move on from here. Okay, so this is that. Now, here are some observations from the flame speed relation that we have derived. The first thing is that the adiabatic flame temperature, TA, being in the exponential, and since the exponential is multiplied by a large parameter, seems to exert the strongest influence on the laminar flame speed. So that reactions that have larger values of heat release have larger values of the adiabatic temperature, and therefore will have a faster flame. And this you can see for example, in this graph. You have three flames, propane, ethane, and methane. This is the dependence on the flame speed on equivalence ratio, which will have a similar, more or less, behavior as the flame temperature. In other words, it peaks near the stoichiometry, and it's smaller on the lead and rich sides. But this is not what I want to show you in this picture. What I want to show you is that since the heat release change quite a bit from methane to ethane to propane, in fact, it's almost double here, and well, 40%, and then it's another 40 or 50%. Then clearly, the larger heat release will have a faster flame speed, and that's what this picture shows. On the other hand, if you, but by the way, those are measurements, right? Those are flame speed measurement as a function of equivalence ratio. If you now look at a different set of fuels where the heat release does not change dramatically from each other, you see that the flame speed also does not change dramatically from each other. And so the dependence on heat release, or the dependence on the adiabatic temperature through the exponential, is probably one of the most or the strongest influence on the flame speed. Incidentally, which is written here, the flame speed also increases with increasing TU. But of course, if you increase TU, you also increase the adiabatic temperature, and so it has, in a way, the same effect, right? In other words, if you start with a hotter mixture, it will have a larger adiabatic temperature, and so so the speed will be larger. Okay, the flame now because of this dependence on SL, the flame will get thinner when you increase Q or TU, okay, which is an obvious result. The adiabatic flame temperature, that's the next item, peaks at stoichiometry. The dependence, however, from the expression that we saw before, right, you can see it here, right, is in fact proportional, because those are written in the denominator as reciprocal, so it's in fact SL is proportional to the square root of LF LO, okay? So that suggests that there will be a shift in the peaking of the flame speed towards the lean or rich side, depending on the Lewis number, right? So for example, as I will show you soon, for hydrogen, the peaking will be towards the rich side. Why? Because on the lean side, the more influential one, the more influential of the two, is the Lewis number of the fuel, which is the deficient in hydrogen, and hydrogen has it's a light fuel and has a larger diffusivity, and as a result of that, it will peak in that direction. Whereas in the rich side, it will depend on the Lewis number of the oxidizer, and that will not be so much affected by the diffusivity. And so here is this result. Actually, there is another thing that is related to the first item. Let's go through that first. So here are the flame speed. Again, it's measurement. Flame speed as a function of equivalence ratio for the same fuel, methane, but in various inert, in nitrogen, argon, and helium. Well, it's the same fuel. It has the same heat release, so you may anticipate that they should have about the same flame speed. But this graph shows you the effect of this other factor in front of the flame speed. Okay? So, for example, argon and nitrogen, they have about the same thermal diffusivity, but the adiabatic temperature is larger in argon because argon has a lower CP, and a lower CP will cause a larger flame temperature, right, from this expression. And so a larger flame temperature will be, therefore, a larger speed. And so you see that it is indeed a larger speed. Now, the flame temperature of methane in helium is nearly that of argon. However, it still has a higher speed, and the higher speed, it's because the thermal diffusivity of helium as a result of lambda and rho, right? The thermal diffusivity is the factor here in the square root, is higher in the case of helium, and therefore the flame speed will be larger, okay? So you see that all these effects that you see in measurement are totally compatible with the relation that we have derived. Now, I told you about the effect of Lewis number. Here is the graph of the laminar flame speed as a function of equivalence ratio. There is a measurement of flame speed, and there is here essentially a calculated adiabatic flame temperature. Did I do it right or wrong? The measured speed, calculate right. And so first of all, this is for methane, and we know that for methane the Lewis number don't change very much from the lean to the rich side. It's very close to 1 across the entire region. And therefore, you can see that there is a correlation, in fact, between the flame speed and the flame temperature. In other words, there is no shift, as I suggested. On the other hand, for hydrogen, if you see the flame speed as a function of the equivalence ratio, there is a shift towards larger values on the lean side and less of a shift on the rich side, and we explained that before because of this dependence on the square root of the product of the Lewis number of the fuel times the oxidizer, okay? So that is shown here. Now let's see if there were some other comment that I missed. Or, yeah, so the next one is the dependence of the flame speed and therefore of the flame thickness on pressure. Well, the dependence on pressure comes because you see in the expression there was a rho burned raised to the n/2 for n was the overall reaction order divided by rho u. So this gives you a pressure of the power n/2 minus 1 that comes from say rho because of the equation of state, right? And so what you see, therefore, is that if the reaction order is less than 2, then the flame speed will decrease with pressure, and most reactions have overall reaction order less than 2. However, the flame thickness will always, because there is an additional rho here, and therefore it kills one of this minus 1, the flame thickness is proportional to the pressure to the negative n/2, and so therefore it will always, irrespective of the reaction order, it will always decrease with increasing pressure. And this is, you can see, for example, result here of the burning velocity as function of pressure, showing a decrease for a whole wide range of pressure. Okay, so in summary, the asymptotic treatment show that the reaction zone may be essentially considered as a sheet across which one must ensure that the variable, namely the temperature and the mass fraction, are continuous, that the flux of temperature, the net flux of temperature and mass fraction are related, right, as we have seen. And in addition, this is the expression essentially that we derived through the reaction zone, that the flux of fuel into the reaction zone must be equal to this quantity in order to maintain the flame steady, right? In other words, for the planar steady propagation, this need to be the flux across the flame. Note that the right-hand side can be also written as essentially a flux, rho u, yu, which is the mass of the fuel multiplied by the velocity, the laminar flame speed, okay? Because in all this expression is equivalent, part of these terms are equivalent to the expression of the laminar flame speed that we derived. In other words, this is just direct substitution. So I want to generalize this to flames which are somewhat curved but not flat, okay? We derive this for a planar flame. And the generalization essentially, I'm doing by hand waving, but this has been derived systematically, at least for flame temperature that are close enough to the adiabatic temperature. They don't vary by much. And the idea is that if you have a curved flame and the curvature is not very small or large, how do we say? It's not very small, right? In other words, the radius of curvature is quite large. Then the flame or the reaction zone surface, if you look at a small segment, it's almost planar, as I'm showing here in this blue box. And so the behavior of the flame in this direction normal to that sheet, it's almost like a planar flame, okay? And therefore, I can apply the same condition across this curved flame with two exceptions or two generalization. One is the coordinate need to be the normal to the flame sheet or to the reaction sheet. I should be more accurate by saying reaction sheet. And the second thing is that I should allow for the temperature not to be exactly adiabatic, but a little bit different than adiabatic, and therefore I will call it TF, because once the flame is curved, there may be a gradient of temperature in the transverse direction or other effect that will lower the temperature or increase the temperature depending on the whatever happened. And therefore, the flame temperature is no longer the adiabatic, but it has this deviation from the adiabatic, which is the difference between TA and TF in that exponential. So this is the generalization that I am suggesting, and I'm going to carry on at least for a few more minutes, and then we will take a slightly shorter break just because you guys came a little late and I am already behind as it stands. So wrong one. I'm going to move to lecture 8 simply because it follow up, and hopefully at some point I will be able to make lecture 7 on detonation that I will be missing. So now the next item is, it really follows from the previous discussion. We are talking about premix flame, and what I want to focus on hydrodynamic consideration, things which will change the flame from being planar or change the flame from being maybe adiabatic. And the first thing is I put back here the generalization that I just mentioned. I don't have to repeat it because I just said it now. And so I'm going to use this as my, my focus of the discussion, at least for a little bit. And then I will generalize this, because this is not exactly this, but I will generalize the discussion. So I will start things in some in a slow pace, ordering things as we go along. So the first problem that I want to address is a flat flame over a porous plug burner. So what you have is the fuel and air enter this tube. Usually this is quite a long tube, so they get enough time to mix. They go through some beads and screen basically to retain a uniform flow. And then they go through a porous plug, and the main reason for the porous plug is essentially because the porous plug well, here it's written, it's essentially serves as a heat sink, because the thermal conductivity of the plug is much higher than the thermal conductivity of the air. Then any heat that is conducted back to the plug, first of all, it's removed by water cooling coils that are usually embedded in that plug, as you see here. And then it maintains the temperature of the plug to be constant, the same as the temperature essentially of the incoming gas. And so here is, well, there is, in fact, the plug also serves not to allow for conduction of products or diffusion of products into the burner. So here is the design of, if you like, of a flat flame burner. And by the way, typically You also introduce some nitrogen here to avoid disturbances from the end and to maintain the flame flat and so on. Those are experimental considerations. So this is the problem that we want to focus on. So we have a given mass flow rate or a given mass flux of fuel and oxidizer or mixture coming out of the plug. It come out as a uniform flow, so you'll have a one-dimensional flow. And a flat flame could be sustained, I say could be, we'll see how and when, could be sustained on top of the burner. And what we are interested is, given M, to find where is the flame located, right? So this is the problem that we are focusing on, and here is the mathematical description within this idea that the reaction sheet can be considered as an interface across which there are jump relations that we know we have derived before and they can be applied. So on either side of the flame, which is located at x equal to xf, then we have to solve reaction-free equations. In other words, the equations, the reaction rate is negligible, so the right-hand side is 0. And these are the conditions across the flame, which is at x equal to xf. Now, what are the boundary conditions? Well, the boundary condition is, first of all, T is a constant, Tu. I have addressed that a minute ago. And the second condition can be obtained from these general jump relation that we have derived across any interface, right? So the interface here is the interface, the top surface of the burner, and since there is no reaction at the surface, the relation that we have derived, I don't have to put it back because it's quite clear, is that the flux of fuel in is equal to the flux of fuel out. So the flux of fuel in is only a convective flux, m times yu, and the flux out also has a diffusion counterpart, okay? So the net flux is the convective and diffusive. And you see the diffusive is, of course, with the diffusivity of the fuel, which is just this script D. So those are the boundary conditions. We have a system of two equations, two unknowns, with enough boundary condition to solve for everything, including the position of the reaction sheet. And so we can solve the equation. They are easy enough because they are, again, second order constant coefficient. They have exponential type solution. And here is the solution written. And if we satisfy all the jump relation, we obtain these two expressions which I have emphasized here in a box. So first of all, the temperature, as you see, increased from this value of Tu to some value Tf. What did I write? Tf, which is less than Ta in general. It's smaller than the adiabatic temperature, clearly. And the concentration go to 0 at near xf. Now, the first relation that we derive is a relation for the flame temperature, Tf. And that all these relations come simply from satisfying these jumps, right, across the reaction zone. And so this relation just read that given a mass flux, and I have normalized this with the mass flux of an adiabatic flame. And a adiabatic flame the mass flux is going to be rho u times the laminar flame speed. That's a known quantity, right? So relative to Ma, the expression gives you that the ratio is this e to the Arrhenius divided by Ta2, right? Because usually this appears as square equal to the difference in the exponential. But anyway, this is the relation. So given m, you know Tf, okay? You calculate it from here. The second relation is a relation for the flame position or the reaction sheet position. And what you obtain that it's equal to essentially this factor multiplied by the log Ta minus Tu divided by Ta minus Tf. Note that m is this m which is given, right? And you can, since this relation is dependent on Tf, if I want to write a relation for the flame position that depends on Tf, then I am replacing m with this exponential, and that's what's written here. So anyway, what I see here is the dependence on xf on the flame temperature. By the way, note from this expression here, which is above the framed one, that when TF approach TA, you're going to get the log of 1 over 0, which is infinity. And what you get is that, it's negative, because 1 over 0 is negative infinity, but this is a negative quantity. So anyway, it approaches infinity, which means that when the flame temperature approach the adiabatic, the flame will be sufficiently remote from the burner. Infinity means it essentially the burner has no effect on the flame. That's what you expect, okay? And okay, so here are the results that I want to show. Oh, before I do that, let me just also emphasize that you see that at the burner, there is a non-zero slope of the temperature. The slope of the temperature is, of course, related to the heat flux towards the burner. So that's the heat loss, QL, at the burner, okay? So you can also compute right away the heat loss at the burner. So here are the results of that expression that show the dependence on the position of the reaction sheet scaled with the, say, the diffusion length here as a function of the flame temperature, okay, divided by TA. And this was calculated for in other words, this is a representative curve for a TA equal to TA over TU is about 6. So you see, as you approach 6, the flame temperature will asymptote to TA, and the position will go to infinity, okay? As you reduce the temperature from the adiabatic, the flame gets closer and closer to the burner. It reaches a minimum distance, and then the only possible solution is that it moves away. In other words, the flame will never be able to reach the surface of the burner. There is always a minimum standoff distance above which the flame will exist. And that minimum distance is connected or is related to the maximum heat loss that you have, which is just sketched here. So QL here as a function of the flame temperature is shown. And here is experimental results that were published in the late 70s by Ferguson and Keck. In fact, they have written from their experimental data an empirical relation which is very similar to this. And here are the experimental results that show again that there is a minimum distance below which the flame will not be sustained in this burner. And this is the calculated value from the asymptotic solution that I have just shown you. The last comment before we take a break is that this is one way to experimentally determine the laminar flame speed. What you do is you measure for a given M, right? M is the mass flux that you can control. So you control the mass flux. You calculate or you measure the heat loss, and so you have values of the heat loss. And and then you extract or extrapolate, because of course experimentally you can measure things up to a certain distance where the flame is from the burner. It cannot go to infinity, but you extrapolate things at zero heat loss, which is essentially when the flame reaches infinity in the model, and from there you obtain the value of the laminar flame speed or the laminar burning rate. Okay, so the next thing I will discuss will be multi-dimensional flames, and after the break we will go into this. Let's take a 10 minutes break. We'll shorten it a little bit so that we can cover a little more. Thank you.